We're going to finish off our discussion of rotational motion, by talking about two topics: rolling without slipping and angular momentum. Rolling without slipping is a special case. In fact, it's pretty much, we're never going to talk about rolling when you're not, or where there is some slipping. It's a special case. So rolling is a combination of rotation and translation. For an object that rolls without slipping, the translation of the center of mass is related to the angular velocity. So by no slipping, we mean that, between the disk and the ground, there is no relative motion. And so in this kind of motion, we have a very special relationship between the velocity of the center of mass and the angular velocity. So the velocity of the center of mass is the velocity that the center of the disk is traveling at, all right, represented by this green arrow. And omega is the angular velocity of the disk's rotation. And so this is the viewer equation. We've used this before, and this is the relationship between these. And we want to convince you that this is true. And so in this first picture, we're following one part of this disk through one rotation, okay, as it goes around one rotation. And so here the little picture is showing you sort of three different pictures of this disk. Here are the little blue dots at the top, and it comes back down to the bottom. So the wheel has done one complete revolution. And so what that means is the distance that it's traveled is 2 pi r. Hopefully that makes sense. That's the circumference. And so as the wheel just rolls once completely, the actual distance that's traveled is 2 pi r. And we take this now and say, okay, so that x distance the center of mass has traveled is equal to the velocity of the center of mass times the time, and that's going to equal 2 pi r. And so we think, what is the time for this to happen? Well, if it does one revolution, we call that time the period t. And so if I solve for v center of mass, I get 2 pi over period t times r, which is just another way to write omega times r. Remember that omega, the definition is 2 pi times the frequency, which can also be written as 2 pi over the period. So that's one way to think about it. Another way is to combine the two motions. So we have our translational motion and our rotational motion. And so let's assume that the translation is going at the speed v center of mass as we talk about. And then over here, we'll assume that the rotation is going with this new equation, v center of mass equals r times omega. And so if just the rotation part of the disk, the center of the disk is not spinning, and then the top part is moving to the right, and the bottom part is moving to the left. If we add up the speeds, so for the top one, I get v center of mass plus v center of mass, that gives me 2 v center of masses. So the top of the disk is moving very fast. For the middle, I take the velocity of the center of mass plus a 0. That gives me just the velocity of the center of mass. And finally, at the bottom, which is kind of the important one, we get velocity of center of mass and then negative velocity of center of mass. So those cancel, and so at the bottom we get that the velocity is 0. This is kind of a hard thing to get, but really this is the definition of rolling without slipping. There is no relative motion between the wheel and the ground, so the velocity is 0. And in order for that to happen, you have to have that relationship. The velocity of a center of mass equals omega times r. Okay, that has to be true with rolling without slipping. So the big key is we can use this viewer equation anytime that we hear rolling without slipping. So as an example of how this can help us, let's say we have a solid disk rolling down the road with some velocity. We want to try to represent its kinetic energy. Now we know we have to have two pieces, the translational and the rotational. But what we can do now is, because we know this relationship here between the angular velocity and the linear velocity, so I know omega equals v over r, so I'll call it big R. And here we're going to drop the center of mass motion just to make life a little bit easier, so we're not having so many things to write. And then if you look up in the book, the moment of inertia for a solid disk is 1/2 mr squared. So here's my equation. And what I do is, for the second term, which is the more complicated one, I plug some things in. So here I plug in the moment of inertia, And then here I plug in this guy, omega equals v over r. Since omega is squared, it'll be v squared over r squared. A couple things happen. First of all, the r squareds cancel. And so the kinetic energy, when you write it out this way in terms of the velocity of the center of mass, does not depend on the radius of the object. And then what we do is get 1/2 times 1/2. Remember, this 1/2 comes from the moment of inertia. It represents how the mass is distributed in our object. And so I get a total of 1/2 mv squared plus 1/4 mv squared. Altogether, I get 3/4 mv squared, where of course 3/4 is bigger than our normal 1/2. So because this is rolling as well as moving translationally, there'll be a larger kinetic energy. But it's much easier for us to write it all out like this than to have these two terms here. So let's try this together. So here's one. So now we're doing the same kind of thing. I have a hollow cylinder now, and I want to know is if I know its velocity of its center of mass of v, how can I represent its kinetic energy in just one term? So give this a go, pause this, and we'll talk about it in a little bit. Okay, hopefully you got D. If you look this up in our book, the moment of inertia is mr squared without any fraction in front of it. The fraction would be 1 maybe if you want to think about it that way. And so here when I write this out, again the r squareds cancel, and I have 1/2 plus 1/2, and so it's mv. Alright, and what you can do, and we'll do this in class, is you can do problems where now, just like we did in chapters 10 and 11, you can do energy conservation of mechanical energy, and using this as your kinetic energy. And it makes life much easier when you write it as one term instead of these two terms together. So now we're going to move on to the last topic we'll talk about in rotations, which is angular momentum, which is tricky, but it's really something that has a lot of applications. And so as you can imagine, everything else we've talked about, there's been a rotational version of it. And so now the last one is angular momentum, rotational momentum. It's we use an L to signify it. Now technically, angular momentum is written as what's called a cross product, and you can read up on that if you want. We won't deal too much with that. But that is the technical definition. But for us, we're going to deal with situations, and the book does this mostly as well, for rotation about a fixed axis. Okay, so when you're rotating when your axis of rotation does not change, when it's fixed, the angular momentum is defined simply as the moment of inertia times the angular velocity. The units will be kilogram meter squared over seconds. And again, this is the analog to linear momentum. And remember, everything is sort of new again, right? And it's just written in our new language. So the mass, the rotational mass is moment of inertia, and then velocity, the rotational velocity is omega. So here's a give it a try problem just to see if this concept kind of makes sense to you. So a solid disk of mass 4 kilograms and radius 0.15 meters is rotating constantly once every 2 seconds. What is the magnitude of its angular momentum? So pause, give this a try, see what you think. All right, hopefully you see that C and D here are the same. Oh well, the answer was B. So here's our new definition. This is in fact a fixed axis, which again, we won't talk about angular momentum about anything besides a fixed axis. And so the moment of inertia for a solid disk, if you look up in the book, is 1/2 mr squared. So for the numbers we have, I get this here for the moment of inertia. Now the tricky part is you need to find out the omega, and here it's not given explicitly, but we tell you it rotates constantly once every 2 seconds. And so omega, 1 revolution would be 2 pi radians, and then 2 seconds, so that gives us a total of pi radians per second. Multiply those two together, I get 0.14 kilogram meter squared per second. Now just like with linear momentum, momentum is really important to us when it's conserved. And so if we start with our new Newton's second law for rotations, okay, so torque equals I times alpha, and we do this, we have the exact same thing we did this with forces, all right, so I can write alpha as d omega over dt. Now if we think about situations where the moment of inertia is not or can change, right, we can sort of blend it back in inside to that derivative if we assume that it's something that isn't going to be changing. And that leads us to this equation here, which was very similar. We had a version a couple weeks ago that said something like the net force equals dp over dt. Well, this is just the rotational version, again written in rotational language. And if we then think about our net torques as being the kind that are external to the system and internal to the system, well, if you're doing a system, the internal torques were always going to cancel out. And so you get finally the external torques equals the change in angular momentum with respect to time. So if no external torques act, angular momentum will be conserved. So this is very similar to linear momentum. It's just that it works for in rotations as opposed to linear type stuff. And so just like before, so our equation says that the external torques equal the change in angular momentum with respect to time. If these equal 0, then I got dl dt equals to 0, which if I graph that, L versus t is 0, that means it has to be a straight line, flat line constant. Okay. Alternatively, if we think about this instead of derivatives as deltas, delta L over delta t equals to 0 implies delta L equals 0, which implies the final minus the initial equals 0, which implies that the final equals the initial, meaning angular momentum does not change or angular momentum is conserved. And so our real technical definition here, again, it's from this equation here, the torques external to a system equal the change in angular momentum with respect to time, the first derivative. And a way to sum this up in one sentence is that the angular momentum of an isolated system is conserved. If you have a system where there's nothing external acting on it, okay, then what that means over here is that means that your torque externals are 0, and so dl dt equals to 0. And then technically, what you can say is when the external torques on a system sum to 0, the total angular momentum of the system will be conserved. So just like with linear momentum, the tough part, I think, with this is knowing when to use it. So let's try some examples. Well, actually, first of all, we'll just sort of briefly discuss about how the equation works. So when you can use this, you can say angular momentum final equals angular momentum initial, which is just the sum of our angular momentums. Again, we're going to use the version that's angular momentum around a fixed axis, which is I times omega. And so if you have the case, which will happen quite a bit, where there's only one object, or I'm sorry, only two objects, then you can just write out like this. So it's I omega for the two objects finally have to equal the sum of I omega for the two objects initially. And we'll do some examples here. The classic example of this that I think hopefully helps people get this, and we'll do this in class, is the ice skater example. Okay, we do it because we don't have ice and everything. We have someone sit on a stool that can rotate freely, and we get them spinning, and we put something heavy in their hands, two masses. And what we have them do is we have them bring their hands in. Okay, and what happens is they end up spinning faster. So they have like an initial rotational velocity, and then afterwards their final angular velocity. And just like the ice skaters on TV, when they bring their hands in, they're going to speed up. All right, and so here's the initial angular momentum, and here's the final angular momentum. And so we can write that out for this person, kind of the ice skater person. So it's got the I final, omega final, equals I initial, omega initial. And then what you can do with this is you can do different things, but what I've done over here is I just solved it for, I said omega final over omega initial has to equal omega initial, I initial over I final. And the thing is, we look in the picture here, okay, here the mass is at a larger distance. So this is, say, R initial for that mass. Over here it'll be really tiny. And so when you bring your arms in, your moment of inertia decreases. So the final inertia is smaller than the first inertia. So this is going to be bigger than 1. We're not sure exactly what it is, but it's going to be bigger than 1. And so like over here, since this I final goes down, in order for the multiplication of these two to be the same, the omega has to increase. Okay, and so the whole idea is with this ice skater is that I omega has to stay the same. So if I decreases, omega has to increase. And that's what you see happen. When the ice skater brings in their hands, they go faster. Okay, let's look at homework style problem. Give it a try here. So we had a disk of mass m and radius r rotates with angular velocity omega initial. So here this disk is rotating with angular velocity omega initial. A second identical disk, which is initially not rotating, is dropped on top of the first. There's friction between the disks, and eventually they rotate together with angular velocity omega final. Which below is true about the omega final they come eventually at the end with? So think about this and answer, we'll talk about it. Okay, hopefully you got 1/2. And so the way I would write this out is just like we've been talking about. So we can say angular momentum is conserved. Why is that? Well, there's nothing external acting on our system. Our system is these two disks acting together. There's nothing outside. Okay, they're only acting on each other. So there will be torques, but there'll be internal torques in between them. And so you dump this guy here, and what's going to happen is they're going to start, you're basically going to slow this one down, speed this one up until they come to some new angular velocity. So right away, hopefully you see that this one wouldn't be possible, okay, because you're going to have to slow the bottom one down a little bit, so the speed's going to have to change to some extent. And then here what you do is you can set up the equation. So initially, I'm going to say the angular momentum I, so for the disk, I'm just going to call it its moment of inertia to be I. And so it'll be I times omega initial. So that's the initial angular momentum. Afterwards, it's going to have 2I times omega final. Okay? And what happens here is since the I's are the same, they can just cancel right out, and you get that omega final equals omega initial divided by 2. Okay, so this is kind of the steps to solving a problem like this. First of all, you realize you can use this. Then you set up your L final equals L initial, and then you go through and solve for what you want to solve for. And let's do one more example here before we take off. So this is a real good application of angular momentum, and it's a dying star. So a star is dying, and what happens sometimes when these stars collide or die is their cores collapse. Okay, so originally its radius is 6,000 kilometers, and it collapses to about 40 kilometers and doesn't lose too much mass. And so if it was rotating at an angular speed of 0.12 radians per second, which is kind of small, what is its speed now? And then the question also asks how many times per second does this thing revolve once it's done. So let's think about this. So here's the problem again. Now see if you can figure it out yourself, and then we'll talk about it. So pause it and we'll talk about this. Okay, so again, angular momentum is going to be conserved here, and the answer I get is A. And so here's the initial case over here with some really big R initial, and here's a little tiny r. And angular momentum is conserved because again there's no external torques. So I'll write that here, no external torque. Okay, everything that happens in this problem is happening because of the gravity of the star, and that's all internal forces, external torques. And so L initial will equal L final. And L initial, now if you look up moment of inertia for a sphere in the book, it's 2/5 m r squared. And so again, the m doesn't change and the r does change. Okay, the r will change from the initial to the final. But that would be my initial angular momentum. It's going to be again I times omega. Right, I times omega, that's angular momentum about a fixed axis. The axis of the star does not change. And so here we set up the initial equal to the final. Now one thing that's nice is that the mass cancels out completely, as well as this weird 2/5 piece. Okay? And when it's all said and done, you get that omega final equals the ratio of the radiuses squared times omega initial. And when you plug in your information, you get 2,700 radians per second. And so what that means is it's increased a lot. And this is what really happens when certain stars die. Okay, they collapse like this, and what happens is the star is rotating a little tiny bit initially, but because of angular momentum conservation, okay, again, angular momentum about a fixed axis is I omega. This is similar to the ice skater. Okay, here the moment of inertia decreases a lot because the radius gets smaller, and so the omega has to increase to make up for that. And if you actually figure this out, omega and turn it into a frequency, it's 430 hertz. And what hertz is how many how many times a second it's revolving. And so these stars, the one we're talking about here, okay, is going around 430 times a second. And this actually does happen. It's a pretty intense thing.